Okay, we're going to look at finding the limit of this one other type of function, which is a piecewise function. And that's just a function made out of different pieces. So we've got one piece here, a second piece there, and a third piece there. So when we're talking about limits of piecewise functions, it's going to be very important about what I would call the joint, or the value where they meet up, where they change over from one function to the next. So like 2 in this case and -3 in this case. These are the types of functions in piecewise functions where we could get like a jump discontinuity. So what's the limit here as x approaches 2? It does not exist, because from the left the limit is 3, but from the right the limit is -2. Since they don't match, the limit existence theorem doesn't apply. The limit does not exist. But over here sometimes they do meet up at the same spot. And when I check the limit from the left and the limit from the right, they meet at the same, or they match up. They're headed towards the same y value. They don't actually get there because there's a hole. But remember, limits don't care. We don't care what it is right at f of 3 on a graph anyway. Right? Limit just means what y value you're approaching. So are they headed to the same y value? In this case they are. So the limit from the left is -2. The limit from the right is -2 as well. So then the limit is -2. Over here the limit from the left is 3. The limit from the right is -2. So the limit does not exist. Okay. So I'm not going to go through this where we have to write the equation for each piece. That was supposed to be a little bit of a review, but we've already had one long video. We're gonna look at we'll just go to the next one. So how do we do it when we don't have a graph? I might refer back to this one when we're doing some of this. But how do we do the limit of a piecewise function? So this function g of x is defined with two pieces, and they switch over at the x value -2. So you can bet your bottom dollar that that is going to be our target value. Yes, it is. Right? X approaches -2, -2, -2. Okay? Notice the function's not defined anywhere at 2. There's not an equal sign in either spot. So that means there's definitely not an f. F of -2 is not defined. That shouldn't stop us from finding the limit. So how do you think we should find the limit? X approaches -2 from the left. I guess that's a rhetorical question because I'm talking to myself. First, I look at my domain restrictions. Which one of these would represent coming up on approaching -2 from the left? It would be the top one, because those are the x values less than -2. So what we're going to do is, this represents from the left because of this. So if I do direct substitution, I'll get the y value that this was headed towards from the left. Right? That would be the same thing here. Whatever this first piece was, if I plug in -3 into it, I would be getting the y value that it's headed towards. Now, if I plug -3 into this function, the second piece, the middle piece here, I would be getting what the limit is from the right, because these are the middle piece are for x's that are bigger than -3. These were for x's less than -3. So that's how we check left and right. This column tells us left or right, and then we just always do direct substitution and we'll get the y value. All right, so when I plug this is from the left, so if I plug -2 in there, what do I get? I get -2 squared times 2 -6. I'm getting 2, I think. Yeah. So the limit from the left is 2. Now from the right, that means my x values are coming in from the right side. So I'm on this piece now, because my x values are bigger than -2. So these would be the x values on the right side of -2. So if I plug -2 into that, I think I get 2. So the limit from the left is 2. The limit from the right is 2. So then I know the limit is 2. So whenever I ask for the limit of a piecewise function, even if I don't ask for the one-sideds, you've got to do them individually and see if they match to answer the limit question. So in this case, they match. They're both 2. So the limit existence theorem says the limit must be 2. If they were different, if I got 2 and 5, then I would have a situation like this where they're going to two different y values and the limit would not exist. Here I notice they're going to the same y value, so that's your limit. All right? So let's work some examples. So I'm not going to do as much of the explanation here. I'm just going to go through them so you can see me work through some. All right, so for this first one, I always try direct substitution. The bottom does not come out to be 0, so that's good. That means direct substitution will work. The bottom is 2e. The top will be ln of e, and I know that ln of e is 1 because they're inverses. So this must have been continuous because direct substitution worked. So because it was a rational type of function, the bottom wasn't 0, so that made it continuous. Direct substitution works. This guy, I'm going to try, they want from the left. I'm going to always try just direct substitution. I don't care about left or right. If direct substitution works, that's the limit, which means if that's the limit existence theorem says it's both sides, left and right. So when I plug in 5, of course, I don't get undefined. I get a number. I think it works out to be 20. So that's what your limit is from the left. That's also the limit from the right if I needed that. I'm going to try direct substitution here. So I'm going to plug in pi for theta. And yeah, again, it's defined, so I end up getting -2. You can pause the video, work these out, and see if you agree. These are direct substitutions, so I'm not going to do too much with the work here. All right, this guy, I'm going to plug in, see if direct substitution works. On the bottom, when I plug in for alpha, I get 5 pi over 3 squared, so that's not 0, so it's going to work. Up top, tangent of 5 pi over 3. All right, so tangent of 5 pi over 3 is -√3 over 2, I believe. And then on the bottom, I just square all that, so I would get 25 pi squared over 9. Instead of dividing by that fraction, I'm going to multiply by the reciprocal. So I get -9√3 over 50 pi squared. Oh, what am I doing? Tangent is not just, you're probably yelling at your device, your computer. Tangent is not just that. It's that over 1/2. Okay. So that's a little bit more of a simplification process here. So instead of dividing by that fraction, I'll multiply that fraction. I think I'm going to simplify the numerator first before I multiply by the reciprocal. Sorry about messing that one up. Let's try again. So I'm going to leave it like this. Up top, instead of dividing by 1/2, I'm going to multiply by 2, and those will cancel, so I get -√3. So now, I'm going to, instead of dividing by that, I'm going to multiply by 9 over 25 pi squared. So that will give me, that's like an over 1, so -9√3 all over 25 pi squared. We're going to try direct substitution here. So I always do the bottom first to see if I fail or not. I don't know why, but that's what I do. So I get 0. Okay, so direct substitution doesn't work. Now I got to find out, is it fixable or not? So when I plug -2 up top, I also get 0. So that means I should be able to tease out a factor of x plus 2 on top and on bottom, because I know that if, I'll do it this way. If f of -2 is 0, then x plus 2 must come out of the top and the bottom. So on the bottom, it's going to be 2 times the quantity x plus 2, right, if I just factor the bottom. And if I factor the top, it's going to be x plus 2 times x minus 3. I'm going to now fix the problem. I should say this with you guys. This is very, very important. I'm going to factor down here. When you're doing this simplification, you have to write the limit every time. You still haven't found the limit. So up top, it's going to be x plus 2 times x minus 3. For full credit, you always have to write that kind of thing on like an AP exam. 2 times x plus 2. These cancel, so now I have the limit as x approaches -2 of x minus 3. So I found my agreeable function. Now I can do direct substitution, and I don't have to write limit anymore when I'm doing that. I plug in a -2. And what do I get? A negative 5 over 2. That's our limit. So this was the first one where direct substitution did not work, and we did our factor method to simplify and get our agreeable function. I'm going to try 3 here. I'm going to get 8 over 9 minus 9 is 0. And they're asking for the overall limit. So what do I know here is a non-removable. That's a vertical asymptote. So we know that that limit does not exist. Now, if they wanted the one-sided limit, like the left or the right, do we do one of those in here? I forget. Yeah, we do. So we'll get to that later. When they want just the regular limit, you're just done if you get non-zero over 0. It does not exist. All right, let's plug in 3/2 here. So up top I get 0. On the bottom I also get 0. So that means that we must be able to factor out an x minus 3/2. Now, if you think back to Algebra 2, hopefully you talked about like if f of 3/2 is 0, the factor would be 2x minus 3. Okay, we could say x minus 3/2, but to make a fraction back into a factor, it's easier to do it this way without fractions in it. So you can think about it this way. We know that x would be equal to 3/2. That would be a solution. If I try to make this side go to 0, I'll get my factor. So how do I make this side 0? Well, first of all, I would multiply both sides by 2. So now I have 2x equals 3. And then I would subtract 3 off both sides. So I get 2x minus 3 equals 0. And that's how I figure out my factor. Okay? So I know that 2x minus 3 must be a factor of the top and a factor of the bottom. So let's see. Well, it's already there on the bottom, so that's good. Up top, I know it's going to be 2x minus 3 times something else. This is a difference of perfect cubes. So there was a method for factoring that. You could Google it. You can watch a video on it. You did it in Algebra 2. How do you factor perfect cubes? So this would be the 2x minus 3 part, and then here we would have 4x squared, we would have a plus 9, and then we would have, I think, a minus 6x in the middle. Let me just verify that. Nope, it's same, opposite, always positive. I forgot that. So then it's a plus 6x. So this is my factor. I'm trying to solve the problem, trying to simplify, remove the discontinuity, trying to fix it. So I now cancel and fix those and get my agreeable function. I'm going kind of fast because you can pause it, you can rewind it. I don't want to make another 45-50 minute video. All right, and now now that I have my agreeable function, I can retry direct substitution. And when I plug in 3/2 into that thing, I'm getting 27. All right, let's try h. Remember, always try direct substitution first. It might work. Don't just start rationalizing the numerator. So if I plug in a -2, I get 0 on the bottom. I'll also get 0 on the top. So that tells me there's a hole. It's fixable. So this is the type where I have to rationalize the numerator. To do that, I'm going to multiply. Remember, think of these as binomials. I'm going to multiply by the conjugate pair. I have to do it on top and bottom so I don't change the function at all. Whoops. Do that again. If I multiply by the same thing top and bottom, all I'm really multiplying by, this purple part, is just a big giant 1. Multiplying by 1 doesn't change the value. Okay, so let's multiply. Remember, our goal is to factor out, to cancel off the x minus 2. Since I know that f of -2 gives me 0 on top and bottom, that means I want to tease out an x plus 2 out of the top and an x plus 2 out of the bottom. So I have you multiply these denominators first, and you don't want, I know it's a binomial times a binomial, don't start doing distributive property like that. You don't want to do that. You just want to keep track of it. It's already factored. The x plus 2 is already teased out. Remember, the goal here is that I need to cancel that with an x plus 2 up top. Up top, I do have to distribute. So I've got a square root times itself is just going to be the same thing without the square root. When I do this times this, I get a positive times a positive. And then when I do this times this, I get a negative times a positive. So I'll get the positive version and the negative version. They'll cancel. Negative 1 times positive 1 is minus 1. So now when I simplify the top, hopefully I can get that x plus 2 showing up somewhere, somehow. That's going to be 2x plus 4, because if I add the 5 and the negative 1, so that's going to work. I can keep going. I can factor that top to tease out. The goal was to tease out that x plus 2. So on the bottom, I've got x plus 2 times the square root of 2x plus 5 plus 1. And on top, I can factor out a 2 and get x plus 2. Here they cancel. So I'm left with the limit as x approaches negative 2 of 2 over square root of 2x plus 5 plus 1. Now I've got my agreeable function. I just canceled the problem. I fixed the problem. I filled the hole. So now I can do direct substitution because this function is now continuous. So I've got 2 over, if I plug in a negative 2, what is that going to be? 1. So then square root of 1, 1 plus 1. So I'm getting 2 over 2. I'm getting 1 for a final answer. All right, let's look at I. I try direct substitution. I get 0 on the bottom. Let's see what type, if it's a whole or a vertical asymptote. I plug in 1 up top. I get 0 up top. So I have removable discontinuity. So now again, this is one where I know because f of 1 was 0, I must get an x minus 1 and an x minus 1 on top and an x minus 1 factored out on the bottom. It's got to happen. So that's easy to see. The bottom's already kind of all set. How do I do it on the top? I want to rationalize by multiplying by the conjugate. And if I do that up top, I also have to do that on the bottom. Whoops. All right, so on the bottom, I don't want to multiply out at all. That keeps becoming the pattern here. I want to leave that x minus 1 factored out because I want to cancel it. Up top, I do the first times the first, and then I do the last times the last. I don't have to do the middles because they cancel out, like I've said a lot of times. So when I do last times last, I've got negative times a positive gives me a negative. A root times itself is just itself. Now, because there's a negative in front, I better put it in parentheses so I remember to distribute that negative sign. Now I can work with the top and try to tease that x minus 1 out of it. Remember, I have to write limit as x approaches 1 every time that I'm doing this simplification. So if I distribute this minus sign, I have 1 minus that plus that. So I get 1 minus 2x squared plus 1 all over x minus 1 times 1 plus the square root of 2x squared minus 1. So up top now, I can do add the 1 and the 1 and get a 2. So I'm going to think of this. I'm not going to rewrite a whole line just for this. It's going to be 2. The top is 2 minus 2x squared. So what I can do with that is I could common factor out a 2. Remember, my goal is I want to get that x minus 1 factored out of the top. Here's a trick the AP test loves to get you with. If I factor the top as is, I would get 1 minus x and 1 plus x, but I need x minus 1. So I would get 1 plus x times 1 minus x. That's not the same thing. 1 minus x and x minus 1 aren't the same. So what I'm going to do is I want to switch the signs of this guy and that guy. So I can factor out a negative 1. So negative 1 factored out times the 2 gives me a negative 2, and now it's x squared minus 1. And I can factor that while I go here. X squared minus 1 is going to be x plus 1 times x minus 1. And the bottom stays the same. So there we go. I factored out the x minus 1. They cancel. That's what was causing the problem, the 0 on the top and the bottom. So I've removed the whole. I have my new agreeable function. So now I can plug 1 into it and see what I get. I can do direct substitution and it should work. I get negative 2 times 2, and on the bottom I get 1 plus the square root of 1. So I'm getting negative 4 over 2. So I'm getting negative 2. This could be a week where you need to show up to office hours to straighten out some stuff. All right, here's one we haven't talked about yet. So, excuse me, we're going to try direct substitution straight away, see what happens. I get divided by 0 on top. I'm sorry, on bottom. I want to see if I get 0 on top. So if I plug in 0, I have 1 plus 0 plus 2 plus 1 over 0. So 1 over 0 actually is interesting here. It's undefined. So this whole thing is undefined, so I'm not getting 0 over 0. And since they don't want the one-sided limit, what happens if I get non-zero over 0? Oh, let me write it out. Non-zero over 0 means non-removable discontinuity, which means a vertical asymptote. And we know when we have a vertical asymptote, the limit does not exist. Now, if it was a one-sided limit, we would do that 0 positive or 0 negative thing to find out, at least from each side, if is it going up or is it going down. Let me just look ahead here for a second. Yeah, that's interesting. So this one, I do want to do one that works out. So I can change this a little bit and make it work. So this one was kind of nice because we got non-zero over 0, so therefore the limit does not exist. I'm going to ask you a different question. Let's change it just a little bit. Let's see, how can I make it 0 up top? If I plug in a 0, I get 1/2, so this will be minus 1/2. So if I try direct substitution, I get 0 on the bottom. I also get 0 on the top. This is one that has a hole. So there's 3 types. When we have the hole, there was like 3 main types that you'll see where you have to do the fancy footwork, the algebra. One method is rationalize the numerator if it has a square root in it. We saw that here and here. Another method is factor if it's a polynomial, right? We did that a couple times here, here, and here. The third method is what if it's a fraction inside of a fraction? That's called a complex fraction. You're just going to basically simplify the fraction. If I have something like 2/3 over 5, I want to write it as a simplified fraction. So that's where we say, that's like a 5 over 1. So instead of dividing by that, we're going to multiply by the reciprocal. So that's basically all we have to do in this case is multiply by the reciprocal. Having said that, before we can so you got to think about this as like over 1. So we're going to take the top and we're going to multiply it by 1 over x, and then things will work out, you'll see. But before we can multiply by 1 over x, we need to combine the fractions up top into one fraction. So this means we're going to have to do some common denominator work up top. So that's how we're going to start this off. We're going to keep that x on the bottom. Up top, we're going to make a common denominator of 2 times x plus 2. Again, I'm not going to go through how to do common denominator work very detailed. I'll do a run through. You need to show up to office hours if you forget some of this stuff from Algebra 2. So the numerator in this first one will be a 2. The numerator in the second one will change to an x plus 2. Don't forget that negative sign has to distribute to both the x and the 2. All right, so now I can combine those 2 fractions up top. It'll be 2 minus x minus 2 all over this denominator. That's how we do common denominator work. I'm going to simplify the numerator even further. I could do the 2 minus the 2, right? Those are just 0. So I get negative x over 2 times x plus 2 all over x. And now I'll call it x over 1. So I accomplished my goal. My numerator is now 1 fraction. Before it was 2 fractions. I needed to combine it into 1 fraction first. And now I can do the multiply by the reciprocal. So instead of dividing by x over 1 or dividing by x, I'm going to multiply by 1 over x, and let's see what happens. So I get the limit as x approaches 0 of negative x times 1 is just negative x, and then I have 2x times x plus 2 when I multiply the denominators. What was causing the problem, by the way? I forgot to mention this all the way back here. If you plug in 0 and get 0, that means it's x. You need an x on the top and an x on the bottom. That's what we're looking to tease out. Because it's like, you can think of it when it's 0, it's like an x minus 0, right? So it just kind of worked out for us when we did this simplifying the fraction. And you'll notice that that happens quite often. This x can cancel with that x because they're common factors. So I'm going to rewrite my limit as x approaches 0 is of this function is now negative 1 over 2 times x plus 2. I now have my agreeable function because I canceled out the issue. This was my problem. I filled the hole now. So now direct substitution shall work. If I plug in a 0, I get 2 times 0 plus 2 is 2. So negative 1/4. All right. Let's go on to our last one here. How many more do we have? Oh, that's not quite our last one. We have 3 more. All right. So they're asking for the limit from the right. So what I need to do here is try direct substitution, because if that works, then the limit as x approaches 2 is, what, like let's say this was 5, then the limit as x approaches 2 is 5, so it's 5 from the left and it's 5 from the right by the limit existence theorem. So we always try this direct substitution first. So if I plug in 2, excuse me, I got to pause this for a second. All right, so I plug 2 into the bottom, I get 0. So I know that I have a discontinuity. Let's see what type it is. I plug 2 into the top. I'm not going to get 0. I don't have to do it out. I know that this part will be positive. I know that this part's positive. I know that part's positive. So there's no way it could be 0. I'm adding 3 positive numbers. So I'll just say non-zero. So what does that tell me? That tells me the limit does not exist because it's a vertical asymptote. But this is one of those situations where they're asking about 2 from the right. So here's what's going on graphically. I don't know what this graph looks like, but I do know at 2, I now know there's a vertical asymptote. And I know there's only 2 options. When the function comes in from the left side, it either has to go up forever or it's got to go down forever. It can't be both because it wouldn't be a function. But that's one of the options from the left. And from the right, it's the same thing. It has to either go up or down forever. So I know that my answer, now we're doing from the right, so let me just focus in on the right side. It's either that green situation, or as I get closer, it's that purple situation, okay? So really what we do here, the idea is I'm just going to pick a number on the right side of 2 that's really close, like 2.1. And if I get a really big positive number, then I know it's shooting up to positive infinity, and that's my answer. If I get a really big negative number, I really should say a really small number, right? Then I know it's shooting down to negative infinity forever, and that's my answer. The point here is that when there's a vertical asymptote and we're doing a one-sided limit, I know there's only 2 possible answers. It's like multiple choice, 50-50 shot, infinity or negative infinity. How do you figure out which one it is? You plug in a number really close to 2, like you can do 2.1, and see if you get a positive number, a really big positive number, or a really big negative number. I like to do that little 0 positive thing. So you could factor it, would make it a little easier to plug in the numbers and figure it out. So I noticed the top probably factors. I think it factors into 3x plus 1 times, that would have to be then x plus 2. Yeah. Right, yeah, that's right. And then on the bottom, it's got to be, that's an easy one. So these cancel, so I can at least work with the simplified function. Now notice that these canceled, I filled the hole, but that's not at my target value. That's at -2. At x equals -2, there's a hole, but we're talking about 2 here. So unfortunately, it doesn't help us. But we do make this function a little more simplified when we try to do our 0 positive thing. So what's a number really close to 2 on the right side? Let's plug in like 2.1. So I usually write it like this, f of 2.1. Up top, I don't care what the number is. I just care if it's positive or negative. I mean, if you want, you can figure out what the number is. Again, I would just plug in 2 and get 6. I get 7 up top. If you plug in 2.1, you're going to get a number slightly bigger than 6. Plus 1 is going to be a number slightly bigger than 7. I don't know. Let's call it 7.2. Doesn't matter what the number is. It just matters that it's positive. On the bottom, when I plug in 2.1, I get a really small number. I don't care what it is. I'm just going to call it really close to 0, and it's positive. So I know that when I divide by a really small number, That makes my number really large. That's a huge idea in math and having number sense. As a denominator gets smaller and smaller and smaller, the number actually itself gets larger and larger and larger. Like I said, if it was divided by this, and then if the next time it was divided by this, and we keep making the bottom even smaller, you can see that those would be larger because this would really be times 10, and then the next one would be times 100, and then the next one would be times 1,000. It would just keep getting bigger and bigger and bigger. So all we really care about is we know it gets larger and larger and larger. We know that it's either infinity or negative infinity. We just have to figure out the sign. Well, a positive divided by a positive is positive. So that's what's happening at that asymptote. All right, let's try this one. We want the limit from the right, so let's just plug in 3. If it works, then that's the limit from the right and from the left. Oh, it doesn't work because I get 0 on the bottom. What do I get up top? 6. I get 11 over 0. That means everything I just said up here. I have a vertical asymptote, so if I think about the graph at 3, as I come in from the right, it either goes up to positive infinity or down to negative infinity. So I know I only have 2 choices for an answer, infinity or negative infinity. So to evaluate this, I'm going to plug in a number really close to 3 on the right side of it, 3.1. And I end up getting 11.2-ish. Again, who cares what the number is up top? I just get that it's positive. And when I plug a 3.1 in on the bottom, I get a positive, a really small positive number. So a positive divided by a positive is a positive, and dividing by a really ever small number gives me an ever larger number. All right, let's try 3 and see if it works. I get on the bottom 0. Up top, I get 11. So this is the same one as before, I notice. Except now we're checking as we come in from 3 on the left. So to find this limit on the left side, we do everything the same, except we're going to plug in a number really close to 3 coming in from the left, like 2.9. So up top, I'm going to get a positive number. I don't really care what number it is. And on the bottom, I'm going to get a negative small number. So any number divided by a really small number is a really large number, and a positive divided by a negative is a negative. All right. Good luck on the practice. Please, please, please come to office hours. And if you can't make those, send me an email. We'll find a time.